information security engineer at Elastic. Endgame just merged with Elastic as of last week, so it's very new and confusing for all of us. First off, a little bit about me. Been working with Endgame and now Elastic for 3.5 years. Primarily, I have experience in reverse engineering, malware analysis, and software dev throughout my professional career. And in particular, with Endgame, I've focused on ransomware protection research over the last few years. In the past couple of years, I've talked about developing decryptors for affected ransomware files, as well as ransom note detection. You can find me on Twitter. My handle is Megerbrom. Brief overview of what we'll be talking about today. I'm going to give a very quick synopsis of ransomware and typical techniques that ransomware uses, and then launch into talking about testing out behavioral ransomware detection frameworks, along with the improved testing approach they'll be introducing as part of this talk. Then I'll get into talking about event data collection approaches for this particular framework, along with giving a brief overview of different analysis techniques that'll be helpful in trying to determine if any of the files that we're seeing exhibit signs of being anomalous. From there, I'll launch into doing a little bit of a demo, discuss automation of this framework, and then discuss some limitations and future work that I have in mind, and wrap things up with a conclusion and hopefully have time for questions. So, very briefly, I assume you probably know by what ransomware is if you're here, but just as a very brief overview, ransomware is any sort of malicious software that's going to encrypt user data. Typically, it will encrypt individual files. So ransomware will launch and enumerate multiple files on your system and encrypt them as it traverses through the system. Any sort of other types of ransomware, like destructive ransomware, including MBR or anything like that, that's going to target raw disk, that's not part of this talk or part of this framework. But it does exist out there. And typically common file extensions are what will be targeted by ransomware. So now jumping ahead, what you'll typically see in ransomware is very specific modification patterns that are evident throughout the file system. The most simple and straightforward is when the ransomware will just simply overwrite the contents of the target files. So in this case, you have sample.doc, but then they're just going to immediately overwrite all the contents there and not rename the file or anything like that. That is the most ideal scenario for someone writing a ransomware detection framework. We'll get into that a little bit later. The second typical modification pattern you'll see is an overwrite paired with renaming of the file. This is usually just some sort of like watermark that they're leaving essentially in the file name in the path to indicate that the file has been encrypted and that they're just trying to essentially announce to the user that their data is no longer accessible. The third pattern is an overwrite with a rename of the file to a different extension, usually a custom extension that pertains to that specific ransomware. Very similar to the first two examples that I just mentioned. And then the last two that you'll typically see are ones where the original document will be deleted and then a new file will actually take its place and be created, and sometimes with a completely different extension and different file name and everything like that. So with a behavioral ransomware detection framework, a typical approach is to have an agent running in the background. You'll have a component that will tap into typically the MiniFilter Driver or ETW for collecting different events on the file system. As these events come through, each each event will be analyzed, inspected to determine if there's any sort of anomalous qualities to that file that the event pertains to. And an alert will also be generated at a certain point once enough evidence has been collected to determine if a process is specifically indicative of ransomware behavior. So for testing of ransomware detection frameworks that are behavioral in nature, typically you'll have a virtual machine snapshot with the agent already loaded, and then the ransomware is moved over to the file system, it's detonated, and then the user is there to monitor any sort of debug output or logs, and then they're essentially waiting for an alert to be triggered. So they're just kind of manually sitting there and waiting for some sort of feedback from the system. So with this sort of setup, there's plenty of limitations. First off is, how long do you actually allow the ransomware to detonate? Do you essentially wait a guaranteed amount of time? Do you give it 5 minutes, 10 minutes, something like that? Do you cap it off at a certain number of files? 100 files, 200 files, 1,000 files. It's pretty open-ended. But either way, if there's a human in the loop, that's an analyst who's sitting there essentially staring at a computer waiting for some sort of feedback and a predetermined amount of time in order to, cut the cord. The second big thing with this sort of setup is that there is a distinct lack of repeatability. Each test may yield different results than the test before, so it's non-deterministic in nature. The environment changes each time depending on what other processes might be running concurrently on the host. Depending on the level of file system activity, the search indexer or some other sort of services could be running in the background that will introduce a lot of noise into your data set. And if you're trying to essentially determine speed to detect in terms of number of files that need to be encrypted before an alert is generated, or some sort of other metrics that you're trying to do in order to do performance testing on your framework, those metrics are going to be unreliable just because of the changing nature of all the background noise. So it definitely makes that a little more difficult to give reliable answers to people that are looking for that, because that's actually one thing that in my time at Endgame that I've been asked repeatedly is, well, here's a new ransomware sample, Tesla crypt, something like that. How long does it take us to detect this? Well, it's a very open-ended question that's always what I lead with, saying that there's just too many different ways that you can answer that depending on the background noise that's involved. So you have to be able to separate that out in order to make a true determination. And as I've kind of alluded to, there is a distinct amount of overhead that's involved in retesting. There's a lot of reverting of your environment. So you're going to revert every single time, because essentially once you detonate, your entire environment's compromised and you can't do any more testing on that specific snapshot. It's a very manual process. There's always a human in the loop. And most importantly, if the code base changes, if you're trying to test out some new analytic or something along those lines, you have to retest everything. You have to go back through all the samples that you've tested before in order to generate those metrics again to determine if you can still reliably detect, whatever ransomware samples that you've been looking at. So that will take a ton of time. So with an improved testing approach, one of the basic things that we wanted to base this around is event traces. And so an event trace in this context will essentially just encapsulate what happens in a file change event, meaning what type of event took place. Was it a file rename? Was it a write? Was a new file created? Was a file moved? Anything along those lines. The actual path involved of the file, as well as content pertaining to the file. So the general idea with having these event traces is that we want to detonate the ransomware one time, and we have that data captured, and we have that for as long as we need going forward. As long as the schema doesn't change in terms of what sort of data we're collecting each time for each event, then we won't need to ever repeat the same test, because we'll have that event trace captured offline, and we can repeat our tests over and over and over without having to revert machines and do anything like that. And so, as I just mentioned, we're going to have offline analysis of the event traces, and that analysis component will produce like an alert score that will essentially tip us off to how much anomalous activity was observed by looking at the individual events. Another advantage of doing this, of using this approach, is that we can filter out noise, meaning background processes, any sort of other like security event logs, anything like that that might kind of get in the way of telling us exactly like how long it's really going to take for us to determine if something is ransomware or not. And as I kind of mentioned already, as we're with the analysis component separated and us able to do offline testing repeatably and reliably, any sort of adjustments to the code base, we can make them immediately and on the fly, and then retest to see what sort of effect they have on our efficacy. And that makes any sort of automated retesting very, very simple and straightforward. So with this new framework in mind, here's a very like high level of what we're kind of proposing. So we have a listener that's going to take in events from some sort of, either from the kernel or from ETW. We want something that's in real time. It needs to be very performant because you're, operating on essentially thousands of file changes, per minute. We need to collect this data and aggregate it along with the contents of the files that are affected. And then separate from that, we have the offline analysis component where we're taking those event trace files and then we're analyzing them and then later on automating them. So for the event trace format, the idea is that we're just trying to collect the minimum amount of information because if this is something we're collecting for every single event that's relevant to us, you can see how that would add up very quickly and introduce a lot of overhead and be a performance drag on the host. We're collecting this very basic information, but then from there, during the offline analysis, we'll collect and derive additional data points that are going to help us generate further metrics that give us an idea as to how anomalous activity actually is. 4 things are all that we're really trying to collect in our event traces. Most importantly, the process in which the activity is originating, the actual operation, the affected path or paths, if it's a rename, remove, along with the actual file contents. So most importantly, getting the event data collection down correctly is the most important step. And this is probably the thing that I struggled with the most here, because my general idea with developing this framework is I wanted something very lightweight, and I didn't want to have to really reinvent the wheel. Because essentially, most practitioners take advantage of like the sysinternal's like suite of tools, including like Procmon, in order for generating this sort of like event data. So I really didn't want to have to go out of my way to do anything like this over again, right? When I first started this, ideally what I wanted was something that was already going to take advantage of like a built-in Python library, because Python's what I had in mind for doing this project. Just something very lightweight, very easy, and able to rapidly prototype and just get moving without having to set up any sort of complicated build environment. So the one distinct disadvantage to using Watchdog, FS Monitor, or anything that I found online is that they rely explicitly on the read directory changes API, which does provide notifications for file change events, but it does not provide the associated process ID. So you might know that a certain file in System 32 is changed and it was renamed and whatever, but you won't have any sort of context in terms of what specific process introduced that change. Was it SVC host? Was it some other background process? Or is it some user-based process that could be ransomware? We don't know. That's the one distinct disadvantage and the thing that rules us out immediately. I spent a lot of time looking into actually using Procmon, and that included trying to actually tap into a direct stream of events from Procmon, because you can set a backing file for Procmon instead of having it rely on its virtual memory. But the disadvantage to that is that the Procmon backing file is in the PML format, which is undocumented as far as I can tell. There's no official documentation, and no one's really tried to reverse engineer this before. So ultimately, I spent a very little bit amount of time of trying to reverse it, and didn't really see much point in making further ground on that. So kind of gave up that effort. Procmon would have been good too for a slightly different use case, but for us, we want to be able to stream the events in real time and not have to kind of replay them, because Procmon would work great if all we're trying to do is just capture one event trace and then just have that offline. But the disadvantage of that is that we need to additionally obtain the file contents relative to each event that would be in the log. So that's something we'd have to kind of go back for. And that's usually not possible or very difficult at the least, because once ransomware is detonated, the system is so unstable that there's really no guarantee that you'll even be able to launch Python in order to collect data on all of your relevant files. Like there's a lot of different things that you have to kind of take into account with your environment being unstable. So back to different collection approaches. Tried using Sysmon, and Sysmon does work great for capturing any sort of new file creation events. But there's no support for file write events. There's a lot of different other types of anomalous activity events that are built into Sysmon, but currently file writes just aren't captured, so that automatically rules it out for our purposes. I looked into using file access auditing. The big advantage to using that is that there's no external components that would be required. But in my experience, it was a little bit too noisy. The setup wasn't very intuitive. And I mean, most importantly, it's very slow. And I still ultimately after that really couldn't get any reliable data out of it. So not saying it wouldn't work for all cases, but at least in my case, this didn't seem to quite work for what I really needed. ETW was something that I spent a good amount of time researching, and I tried multiple different libraries in Python that would help out, including PyWintrace and PyWindows thingies. I love that name. But as with file access auditing, the results were not very consistent. And most importantly, the traces were taking way too long to generate, along with just introducing a significant amount of overhead on the system. So a couple of things there that really took that out of the running as much as I really wanted to use it. So finally, my last option was to build my own MiniFilter Driver. It's by far the most performant, I think, of the approaches that I'd looked at. But on the other hand, it's the most complex and potentially unstable. I was trying to avoid this at all costs because I'm not a kernel developer. There's just so many wrong things that can happen if you're developing a MiniFilter and just working around the kernel and introducing blue screens and other instability in the system. But it was something I had to undertake just because of lack of options. So with the MiniFilter driver in mind, we'll revisit the framework that I'd already mentioned before. So with the MiniFilter and us operating in the kernel space, we're going to reduce the complexity of that initial listening component. So all we're going to gather from the MiniFilter is the process ID, the operation for the event, along with the affected path or paths. We're going to take this content and write that out to a custom log file that we're going to save. But that's all we're going to do with the MiniFilter driver. We don't want to introduce any sort of additional file reads. We're not going to read in the content or write that content out to that log file. We're trying to keep it essentially as simple as possible because of the high risk, essentially, of operating in kernel space. And I mean, that's more just me kind of looking out and trying to cover my own tail. For the collection, we're essentially saying that's going to be a component that will run in user space. That'll be a Python script. And essentially, we're going to just tail the log that's generated by the driver. We're going to take each event as it's streamed in, obtain the file contents that are relative to that event, serialize that data using Pickle, which is a built-in Python library for serialization, and then we'll write that serialized data out for each event to disk in a separate log. And then the analysis will take, that will be a separate component, as I've mentioned before. That's going to be a separate component, also written in Python, that will take in the log files that are generated by the collector, and then we'll be able to do our offline analysis that way. So through our analysis, there's a few high-level objectives that we have in mind here. First off, we're just trying to read in the event trace file. Pretty simple there. And we're going to deserialize the events in order as they took place, which is very straightforward because if you just read the file in from top to bottom, from beginning to end, the events will be in order because that's how they're written to disk. So then for each event, we're going to produce any sort of score that will indicate to us how malicious that activity or how anomalous that specific event looks to us according to the metrics that we have written out. We'll take that score and it will be compared to a predetermined threshold that we're through tuning that we've kind of come up with, or you can kind of just pick essentially a number out of the air and do the tuning on your own. So then with that threshold in mind, we're going to output a final score once you cover all the events captured in the trace, and then you'll have you can do a final determination of whether or not the activity is ransomware or not. So I'll cover 2 or 3 analysis metrics that are encapsulated currently in the framework. You can definitely introduce a lot of your own, but these are pretty essential building blocks to getting a reasonable estimate of high-level ransomware activity and kind of go from there. First off, entropy. If you're not familiar with entropy, very short, straightforward definition is it's just a measurement of the randomness of the data. So how is that relevant to us here? High entropy is typically, not always, but very typically associated with encrypted content, because essentially if entropy is a measurement of the randomness of the data, encrypted data also tends to be highly random in nature. And so plaintext files, let's say, are very, very low in entropy because, let's say if you're talking about just English specifically, text files, HTML files, CSS, anything like that, is going to have very low entropy because it's only using such a narrow range of the typical bytes allowed. If you're talking, there's 256 different possibilities for a byte, and we're narrowing the space of that to the first 128, then the randomness of the data is not really going to come through that much. On the other hand, compressed data, so zip files, anything with PK header, docx files, 7-zip, that's going to come off as high as well as encrypted data. So there's actually been some research into trying to delineate between compressed data and encrypted data. Don't really get too much into that with this sort of research here, but it's at least something to keep in mind. And as I mentioned, encrypted data is typically very high in nature in terms of entropy. So how does that all relate to what we're looking at? Well, so we're not trying to pick out very specific examples of like this number looks very off to us or whatever. What we're looking for is a general trend for a process of files that are being modified by it, all sort of exceeding the typical expected entropy range for that file type. So as I mentioned before, text files, HTML files, anything that's going to be raw text, that's the sort of data that you're going to see if the files are being directly encrypted. You're going to notice very high swings in the entropy that result. So a text file should be very low entropy. After it's encrypted, would be very, very high entropy. But that happening to one file on its own is not enough to really sound the alarms. You need a consistent trend of that across the board in multiple directories to multiple file types in order to truly ascertain whether or not there is a actual trend taking place. The file header is also another very important part to look into. So the way we get information from this is that with more standardized formats for file extensions, like docx, doc, PDF, anything along those lines, they're going to have very well-documented headers and magic byte sequences that we can reliably point to and say, this is a ground truth, this is a .pdf file, should start with these 4 bytes all the time. And if it isn't, then that's something that we need to be aware of. Now, as I kind of mentioned before with the entropy, it happening to one file is not enough to determine if there's a trend or not. You need to see that sort of activity take place across multiple files in separate directories, things of that nature. Like you need to see more than just 1 or 2 files changing in order for us to really determine if something nefarious is happening. So yeah, headers are a very reliable indicator for us. And this relates back to the first 2 metrics, but in file rename operations, what you'll typically see with ransomware is, as I mentioned before, a lot of the files will be encrypted and then they'll be renamed, or they're renamed and then encrypted. So sometimes depending on the latency involved with, the communication from the filter driver, through the log file, to the user space component for Python, you might not even be able to go back and look at the original file because the file has since been renamed. And if you don't get the rename operation and all the event data according to that, you won't know the new name of the file. So you need to capture that rename event, and then you'll know that that you can have the context of, this is now a .ransom file, but before it was a .doc file. And if you have that context, then you can make the comparison to say, okay, we have this file. It used to be a doc file, so let's compare it to any sort of doc headers we know, and let's compare it to the typical entropy range that we would expect for this file format. So it's a very subtle little thing, but something that definitely gives us a little more ammunition. All right, so now time for a quick demo. Let's see. All right. Let's see. So I've already installed the driver. This starts the service for the driver. We can see some debug output there. And this starts the user space component that's written in Python. So all this is going to do is just read in essentially what we're streaming out to debug view here. This isn't the exact data that's captured. It's a more well formatted version of what's captured in the logs. But this gets the point across that the two are communicating through the log file, and so essentially all the Python's doing is just reading in the log file that's generated by the driver. So nothing surprising there, but at least it works. Okay, so now what I'm going to do is I have a specific hash of a piece of ransomware. It's Globe Imposter. If anyone's familiar with that ransomware family. I'm looking up the hash on my file system, and I am going to proceed to launch the ransomware. And so you can sort of see some events slowly coming through here. Of course, the filter driver is seeing the events, and you're seeing multiple write events because that's usually what comes through, is that it's not ever just one clean file write and that's it. File write operations usually take place across several operations. So we see some of the output coming through in debug view, but then now we're seeing a lot more of that output coming through in our other window where the collector is running. And so we already actually put in an event cap. So we're capping the capture at 1,000 different events. And now, just because the ransomware is introducing all sorts of craziness into the operating environment, I'm going to suspend it just to, essentially just kill it for the time being, just because it's slightly annoying and introducing a lot of slowdown. And what we're going to do is we're going to rescue our log file here. It is written to Python log, and right there, pythonlog.decart. So the file system, at least in this case, is still relatively stable, but it's not at the point where we can really rely on it for anything more than just collecting our log file and moving on. As I kind of mentioned before, the stability environment is very much in question, and several times before, through testing this framework and in the past, it's just I've had all sorts of user space processes just terminated directly by the ransomware. I've had log files corrupted by the ransomware. There's just a lot of different things that can happen when ransomware is just going through and essentially blowing away any sort of artifacts it can find on disk. So all we really need to do is just exfiltrate the log as quickly as possible once we've determined it's analyzed enough events, and then we can kind of move on from there. Let's see. So I have my log file here. And I'm going to write it out to disk. Not there, but here. Okay. Let's see, where is that? Oh. Okay. So what we have here is what we're seeing, it looks like a lot of data coming through. You can't really make any sort of determination of what's going on just looking at it so fast. But we're looking at every single event that was captured in the log file and breaking it down, with our high-level metrics that we mentioned before. With this in particular, what we're seeing is, so here's some of the initial noise that we just saw in the background that wasn't relevant to anything other than just a steady state for the environment. But after that, you'll slowly start to see files being modified in different anomalous patterns, and we will tip that off in certain cases where we have enough background on the file extension involved. So right here, you can see this file with the random name, but a .text extension has an entropy value of 7.91, etc. That far exceeds what we would typically expect for a text file, and so that's something that we would mark as anomalous, and that would contribute to the alert score in our specific case. The same thing with a HTML file here. This particular JPEG file, a little bit below that, that's something that sounds off even more alarms, because not only does that exceed the entropy range expected for a JPEG file, which would be higher than a text file typically, but it still exceeds the range that we would expect for that particular format. If you then take into account the JPEG header, and that also we notice a mismatch there, that's something that's going to be very highly indicative of anomalous behavior. Seeing an entropy mismatch as well as a header mismatch. And if we see that sort of activity across multiple events, then that's something that we would, definitely determine to be anomalous very quickly. So we captured 1,000 events, but you don't really need 1,000 events in this case. You can make your judgment much earlier, but it's more just for posterity that we collect all these events, because we're detonating this piece of ransomware one time and we're moving on and we're never doing it again. But we have all those events, and we can filter out any of the extra noise. We can determine an earlier threshold to cut things off. It doesn't matter. We just have that data and we can play around with it as we need to. And just for fun here, let's see, I got a couple other samples I can at least analyze through without detonating, because the detonation takes a little too long. Let's see, so we have BTCware. This is another common family. And so with this one, we didn't capture nearly as many events, just because I think this earlier on, I might have actually just let this run for a certain amount of time, and then I think I just Control-C and closed out the Python agent that was collecting the events, just because the environment was starting to become unstable. But with this particular sample, the activity sticks out right away because there's file renames involved. And so with some of this activity here, like you can see that these are .header files, with a pretty interesting file extension there. And you're noticing that you're going from a legitimate known extension type, which is .h, to a completely unknown extension, and you're doing it across the board. When you're taking multiple different file types and you're renaming them all to the same file extension, that's something that also would stick out, and that's something that we can kind of alert on as well. But you see that activity taking place in multiple places, and like here is where we have a .exe file that's also being subjected to the same sort of activity. And like that in particular would stick out because you're expecting an MZ header for any sort of executable. But in our case, that will definitely not be an MZ header. And then the entropy will probably exceed what we're expecting for an exe file as well. So a couple of different layers of activity that we're kind of looking for there. Let's see. And so there's also one, and this one is just because of, like, this kind of alludes to what I talked to before. But so with cancer, that's a specific ransomware. It's not, I wouldn't say it's too common, but this is definitely one that stuck out for me a lot because I've tested it multiple times. But in this case, what you'll see is that there's not as many things, like the alert score that it's determined, essentially, just kind of throwing numbers out there, but like, if there's a header mismatch or an entropy mismatch that counts for like 1 or 2, we analyzed almost 900 files and we only essentially tipped off on 6 different files. So why is that? Well, in this case, what you can see pretty quickly is that we actually output the length of the contents that we read in. And by default, we're only reading in 2 kilobytes of the file, just because that's a nice kind of round number and not something that's going to tax us and essentially overload the system while we're trying to stream these events. Either way, we're reading in this amount of data, and in each case for all these different file types, all you end up with is 7 bytes of data and the exact same entropy value, 2.52, etc., in each case. So in this case, it's not even ransomware. Like, I looked into this activity a little bit more. They're essentially just corrupting the data, putting some sort of little watermark in there, and then moving on. And they're doing that to every single file that it comes across that matches its the range of extensions that it's looking for. In this case, it's definitely something that's more just destructive, and there's really no intent to restore the data, provide the means to restore data for ransom. But it's something more just kind of curious just to look through. But I'll actually show you real quick just because it's so obnoxious. Let me see if I can find the... Let's see. So this. Yeah, I can't really find it. But yeah. Anyways, it's a very destructive ransomware sample that just compromises the environment like almost immediately and essentially renders it unusable. Let's see. So, okay. Okay. So automation is pretty simple in our case here. All the traces, we can just store them in a central repository and just periodically rerun our latest analysis code base against whatever we have for traces in that repo. You saw how easy it was just to take one of those traces and invoke the Python interpreter and launch our script. In order to do that analysis, it takes place in a couple of seconds at most. And then we have that data as long as we need to, and we can, break that apart however we want to. And that's something that we can easily track over time to see how our efficacy would be affected by certain changes, and just kind of tracking how we respond to different families that we might also introduce later on in the system. Let's see. So there are definitely limitations to this approach. As it stands now, one thing that we'd have to take into account are ransomware samples that utilize multiple processes for encryption and deletion of the files. Locker Goga is one of the most common examples of this sort of activity. And essentially what that does is it will launch an independent process to handle encrypting one file and it'll also launch a separate process to delete one file as well. This comes off as extremely noisy and introduces a lot of overhead and noise into the system. But for our purposes, it becomes a little harder to track that activity because what we're typically looking for is one process modifying multiple files in an anomalous way. What we would have in this case is we'd have one process modifying one file and then being immediately terminated, and then a separate process being spawned, and so on and so forth. You could tie this activity back to the parent process that's launching all these child processes to enact the encryption and deletion, but it's something that we would have to do in the analysis stage to kind of correlate that activity. We'd have to modify the event schema to take into account parent process if we wanted to look into that and make those correlations there. It's something that we could definitely analyze and connect the dots on, but the framework would need to be changed a little bit to accommodate that. There's one case, I completely forget the family that it's associated with, but I've seen it where essentially multiple files are deleted across the system, and the details for actually decrypting that data, they're all jammed into one archive stored in the temp directory. So this temp file in the temp directory just builds up pretty quickly over time to something in the tens of megabytes, if not hundreds of megabytes, very quickly, just because all it's doing is essentially taking in an encrypted compressed format of the affected files. That's not something that's seen very often, but it's something that we would need to try to figure out in our analysis if we could try to sniff out that sort of activity. A few different ransomware families will skip over the file editors to essentially try to subvert the sort of analysis that I mentioned with mismatching headers. It doesn't happen very often, but it's still something to be mindful of. So while headers provide us a lot of valuable data, they're not the be-all, end-all, and that can't be our one silver bullet all the time. We're going to have multiple different metrics and a layered approach to sniffing out this sort of activity. And finally, there is also there are cases where encryption won't introduce higher entropy. I don't see this very often, and there's only like one sample I can actually think of that does this. But it's also something to think about. And as I mentioned before, our user space component is essentially under attack throughout the detonation of the ransomware. I've seen it happen a lot of times before where the Python libraries will be encrypted as they're executing, and then the Python process will crash. If that's something that you don't have to worry about because it's not going to reach it until later on, possibly, but we need a better way to arm our process from essentially the ransomware that's being detonated. So there's a little bit of future work that needs to take place for this framework to be a little more usable. First off, I need to post the source on GitHub. Need to get around to that. I will mention that the Elastic Endgame merger is slowing that up a little bit, so that's a pretty convenient excuse for me. So it'll probably be a few days, if not a week or so, until I can get this get the code posted. But if you follow my Twitter, I'll definitely post a link to that when it's been posted. I definitely need to clean up the driver code. It definitely needs a lot of work. I am completely amazed, actually, that of all the work that I did on the MiniFilter driver, that I didn't crash a box one time. It should have blue screened multiple times, but somehow everything I was doing was at least close enough to what I needed it to do, that I wasn't doing anything like totally corrupting and blowing up the system. So need some more work, but yeah, something that you guys can pick apart once I post the code. The collector script, speed as well as the CPU overhead involved is a surprising amount for all we're doing is just reading in a log file over and over and writing to a separate log file over and over. There's a little bit of overhead in that, so I would definitely like to streamline that a little bit. Marie mentioned the process protection for the collector. I'd like to look into ways I can protect our Python process. A better means for log exfiltration would be very convenient for us. This is as simple as setting up like a shared folder in VMware and essentially cutting off access to that through for all processes except for our Python process. And something simple like that would work. An automated method for pulling down magic byte sequences that have been posted online would be great. There's definitely a few different repositories online of this sort of standardized header data. If we can tap into that and just pull that down, that would save us a lot of trouble of having to kind of manually go out and scrape that sort of data, port it over to Python and use it. If we just had a way to scrape that automatically and pull it in and get it updated, that'd be amazing. And then taking a lot of the event traces that I have stored offline and posting those, that'd be great. I think that'd be a good place for everybody to kind of start from. And then finally, going back to Procmon, it would be nice to actually have a way to take Procmon log files, and these would be not PML files because, as I mentioned before, those aren't documented. But taking the PMLs translated to CSV or XML, taking those files and then having a collector that essentially will read those files in and then try to go and obtain the relevant file data and package that up into one specific event trace that we can then use to feed that into the analyzer. This approach could work, but essentially relies on the system being in state, because you would need to not only capture the Procmon file in the first place, have it still usable, to have it convert to the CSV or XML, and then from there launch a separate process to do the translation from that and the collection into a separate event trace. So it's possible, but I think just due to the stability in the environment, it'd be a little bit of work, but something fun to look into. So to wrap things up, if we decouple our components, it's going to allow us a lot of flexibility during our testing. If we keep the standardized event schema, then we can do the test multiple times, repeatedly, over and over, and track changes and any sort of effects to efficacy over time. And as long as, we're archiving our event traces, all we're ever going to need to do is detonate our ransomware one time and never do it again. All right, thanks.
Do we have any questions?
Hi, nice presentation.
Thanks.
I can recall a similar presentation in VB 2015, right? But good thing is like now you're sharing the code, right? My question to you is, do you have any statistics on how many ransomwares or could be identified by this method? Because definitely there is as you mentioned, like if the offset is changed.
Yeah.
And I believe like the new ransomwares are targeting that.
It's hard to pinpoint a specific number of, this detects X amount of families or this percentage, but I mean, I would venture to guess it captures more than 50% just based off of the number of families that I've seen over time. It would just need more adjustment to take into account like those kind of edge cases I was talking about with, families like Locker Goga that, introduce more processes that kind of convolute things a little bit. But yeah, this is definitely a good building block, I think, to getting started on having an effective framework.
Any other questions? Yep.
Hi, good afternoon. I just wanted to ask, like, if I'm, let's say now I'm a data analyst, and I want to know what I'm supposed to do before even the ransomware gets to our environment. Like, how to prevent it.
So ideally, with ransomware, like, even if you have a detection framework in place, there's still the potential of enough data being corrupted before detection that you have so much data that you need to recover, that backups are pretty much what you need. So having like an effective backup strategy, I think, is the most ideal scenario. Like automated backups that can be stored offline, in separate, even just like USB drives, anything like that is the most reliable thing in order to recover reliably from a ransomware infection, just because the detection, even if it's covering 99% of the ransomware out there, if you get hit by the 1%, it can still wipe out enough of your data, on your servers that, are still going to be kind of, left scrambling to try to recover that data. So yeah, having an effective backup strategy is, I think, the number one thing you can do. You can also introduce, more strict access modes, at least for like reading or writing data on very specific directories. If you have data in particular that you really need to protect, so I think just more strict auditing of file access, I think that can help out a little bit. Yeah, I mean, there's definitely a few different things you can do, but I think backups is the number one thing for me.
Thank you.
Mm-hmm.
Any other questions? We have a few questions on Slido.
Oh.
The first one is, do you trace all the events in a given chain, or do you select reliable ones to avoid potential false positives? How do you deal with common events which can be performed by the OS?
So at least right now, with the way the framework's set up, there's no specific tuning out of some of that background noise. I kind of left that open-ended because if you get down into the weeds of trimming out different event files and stuff like that, it might not be the same across multiple OSs. So you want, in different versions of Windows and whatnot, like that's some tuning that you'll want to do in your specific environment. So you'll want to run this multiple times and even just have it running without any other specific external processes that you've launched, just to see if you can get a steady state for the system. And then you can tune out the EVTX files and do whatever you need to in order to reliably have only the events that you're concerned about popping up. And if you're only looking at, say, one specific process, then that's something that you can do in the analysis stage, where you can restrict the analysis specifically to one PID. Yeah, there's a few different ways that you can kind of handle that, but the advantage of having the event trace file and working off of that is that you can tune that noise out immediately, without having to redetonate the sample and make adjustments and rebuild everything and deploy your new sensor or whatever.
And the next one is, have you looked at using honeypot files and prioritizing them for the specific operation you expect ransomware to perform, such as file names starting with exclamation marks or file size?
Yeah. I've definitely looked into canary files, I think is what they're referred to a lot. Yeah, I really do like the idea. I just haven't specifically, tried to introduce them into this framework or use them in any of my research so far. But yeah, I've definitely heard that they're very, they can be very reliable if they're deployed correctly.
Okay, thank you. Before we end, any other last questions? Okay, let's give Mark another round of applause.